Hello everyone, welcome to Revamp Physics Tutor YouTube channel. This time around we are going to be looking at standing waves in a stretch string and air column. That is standing waves in string and pipes, both closed and open pipe. Basically in this video what we are going to focus on in solving calculation problems that probably we can come across in examination such as WAEC, NECO, GCE, NECO GCE, and our UTME and some other examinations. But before we do that, we will quickly do a brief introduction into this topic. But in case you need a comprehensive explanation on this topic, we have a book prepared for students preparing for any of the exams mentioned before earlier in the video. So you can reach out to us on any of the number that will be displayed immediately after this video, and we can discuss how to get the document across to you. The document is designed for students in year 10 to year 12, that is SS1 to 3 students. And that document explains a lot about all the topics in physics, and it's very, very brief and precise. It's just like a student note that is designed for the student. Okay, now let's quickly consider standing waves in string and air column. Now we start with the string. Now when string is fixed at both ends and the string is set into vibration, the fixed end of the string is referred to as nodes, while the most displaced part of the string is referred to as antinode. As we can see on the screen, we have a string here set into vibration. We can see that the fixed end is known as node, that is the point where we have a minimum displacement or no displacement at all, while the center of the string is known as antinode, where the position for maximum displacement. This is the string, but when you set string into vibration, you know that the string vibrates in this pattern, and that is what we have in that diagram. And this represents the length of the string. And when string is vibrating in this mode, we'll say the string is vibrating in first harmonic mode. That is when string is vibrating with just a single loop. That is what we call first harmonic mode. And when string is vibrating in this mode, we call it second harmonic mode. And this third harmonic mode, and there are some other names that they can call it. You can see right on the screen. Now, what are the common questions here? In your objective question, they may ask you when string is vibrating at the first harmonic mode, it will have how many nodes and antinode. From the screen you can see in first harmonic mode we have 2 nodes and just one antinode. So also in second harmonic mode we have 3 nodes and just 2 antinodes, and like that we can continue like that. And when it's in fourth harmonic mode, you know you're going to have 4 loops, and you can use that to interpret any question or solve any problem you have there. Now what is important to us is to solve some calculations question here. Now from first harmonic mode that we have on the screen, when string is vibrating in this mode, this length L from here to here, length L is equivalent to half of a wavelength. It's equivalent to half of a wavelength. This is part of the discussion that we will have come across in the class. Now, if L equal to half of a wavelength, it means we can easily say that our wavelength equal to 2L, and that is what we have here. And we all know that wave in the string also obey general wave equation, which is V equal to F lambda. So using this, we can say our V equal to 2FL because our lambda equal to 2L. And substituting this into this equation, we are going to have this. And from here, we can make F the solute of the formula, and this will give us F equal to V over 2L, and this frequency here is known as a first harmonic frequency, or we can call it fundamental frequency, and this is the minimum frequency, the only the minimum, the least frequency that a string vibrating can produce. That is a vibrating string. The minimum frequency that the vibrating string can produce is known as fundamental frequency, and the expression for fundamental frequency is what we derived here, and that is what is on our screen here. So for the string vibrating in second harmonic mode, you can see, if we use the knowledge of what we did here, you can see that the length here, our length here, L, will be equal to half of a wavelength plus half of a wavelength, which makes our length to be equal to a wavelength, because half plus half will give us 1. So, and that is where this one is coming from. And from this one, we know that easily we can say that our lambda, we can say our frequency will be equal to V over L, from V equal to FL, V equal to F lambda rather. From V equal to F lambda, we can say our frequency equal to V over L. And the string vibrating at this mode is in second harmonic mode. Therefore, our frequency will also be second harmonic frequency, or we can as well call it first overtone frequency. So you can see the expression here. But if you look at this relationship very well, this is second harmonic frequency. If you look at the relationship between first harmonic frequency and second harmonic frequency, we can say that our second harmonic frequency equal to 2 of our first harmonic frequency, and that is the expression we have here. And this gives us the harmonic series for a vibrating string that we're going to consider. So without wasting much of our time, similarly, we are able to generate expression for the string vibrating at third harmonic frequency, which means that the string vibrating as fourth harmonic frequency will also equal to the product of 4 and first harmonic frequency of the string. So it continues like that. For fifth harmonic frequency, we have F5 equal to 5 F1. So that is the harmonic series for vibrating string. So let's quickly use this in solving problem. Okay, the first question that is before us says a violin string that is 50 centimeter long has a fundamental frequency of 440 Hz. So we have to calculate the speed of the waves in this string. Okay, now according to the question, length equal to 50 centimeter. Taking down 1 to meter, we have 0.5 meter. And we have the fundamental frequency given as around 40 Hz. That is our F1. So we have to find the speed in the string, the speed of the waves in the string. If you remember what we derive, our speed for string vibrating in first harmonic mode is given as this. So substituting the values, the parameters given in the question, we're going to have a 2 multiplied by the fundamental frequency, which is 440, multiplied by the length of the string, which is 0.5, and we have the answer as 440 meters per second. Now, moving away from that, we have another question here that is talking about some parameters that can be mentioned in stress string. When you stretch a string, we have a parameter such as tension in the string. Also, we have another parameter that is represented with mu here. That mu is mass per unit length. That is mass of the string over the length of the string. That is what this mu represents. And all these parameters, they have a relationship. That is when the string is vibrating in fundamental frequency mode, F1, this frequency is directly proportional to the square root of the tension, and inversely proportional to the square root of mass per unit length, though you can get all those ones from your textbook, or you can request for the document I mentioned at the beginning of this video. But we are looking at calculations here. This second example says, ask us to calculate the fundamental frequency of a piano wire of mass 5 grams and length 25 centimeter under a tension 200 Newton. Like I said, this is the relationship between the frequency, tension, length, and mass per unit length of a vibrating string. So we can substitute all the value given into this formula, and we are going to arrive at the answer. Okay, using these parameters, we first calculated mass per unit length using this formula, which is mu, which is represented with mu, and that is what we did here. Mass per unit length, the mass of the string is 5 gram, which is equal to 0.005 kilogram, as we can see here. And the length of the string is 25 centimeter, which is equal to 0.25 meter. So mass over length will give us a 0.02 kilogram per meter, bringing that value into this formula here. So we have 1 over 2 multiplied by our length, and we have 200 divided by 0.02 under the square root, and we arrive at 200 Hz for our fundamental frequency. Let's say in case you are asked to calculate the force to photon frequency for this particular question, just use your F2, which is force to photon frequency. F2 will be equal to 2F1, or let's say we are to find a second of photon frequency, which is a third harmonic. We can just say F3 equal to 3F1. We don't need to start memorizing too many formulas. Just always remember the harmonic series of a vibrating string. Okay, moving away from this example, we go straight to another example that we have here. The example here says the guitar string 50 centimeter long has a fundamental frequency of 200 Hz under a tension of 30 Newton. So the tension in the string is adjusted so that it can produce a new frequency. So we have to calculate the new tension if the length of the wire is kept constant. Now, from the expression that we just looked at now, F1 equal to 1 over 2L root tension over mu, we can deduce that our frequency is directly proportional to square root of our tension. That is, we can say our frequency is directly proportional to the square root of our tension, and from here we can say frequency over square root of our tension equal to a constant. So using this idea, now if our first frequency is 200 Hz, and the second frequency according to the question is 400 Hz, we can see them here. So the tension that we have when the frequency is 200 is 30 Newton. We have to find the tension when the frequency is 400 and length remain constant. And if length remains constant, it means every other parameters in the string will remain constant. So substituting these values into this equation here, we have this. Okay. Now, making use of this relationship, that is F equal to constant multiplied by root of t, and that is, we make our k the set of the formula. We have F over root t, and that is what is happening here. That is why we have a 200 over root 30. 30 is our tension, and that gives us the value of the constants to be 36.5. Now, if this is our constant, it means we can say F1 over root T1 equal to K, and that is also equal to F2 over root T2. And that is what we applied right here. And here we have root T2 equal to F over K, making the root T2 the subject of the formula. In the second instance, we have root T2 equal to F over K, and that is what we did here, and that gave us 10.95 as the value of root T2. And to get the value of our T2, we have to square both sides. By squaring both sides, we are able to arrive at this value for our root T2. Okay, now let's move away from this and go to pipes. Like what we look at in the strings. In our pipe 2, we can have a standing wave set up in our pipe. Now, first one we are considering is open pipe. In an open pipe, it means both ends are open. And in this case, the sound wave, we have freedom on both ends, and that will create an antinode at both ends while we have our node at the center. This is opposite of what is happening in the string, but at the end of the day, we are going to have the same harmonic series, because as you can see, from this point to this point is equal to a quarter of a wavelength, as you can see, and from this point to this point is also equal to a quarter of a wavelength. So if you actually work on that, you are going to have the length of the pipe here. You're going to have the length of the pipe here equal to half of a wavelength, because quarter plus quarter will give us half. So also in an open pipe, we have lambda equal to 2L, like we discussed in string, and our F1 will also be equal to V over 2L. Similarly, we have F2 to be equal to 2F1 and F3 to be equal to 3F1. Let's quickly apply this in solving. Okay, before doing that, let's discuss our closed pipe and just solve the problems together. In the case of our closed pipe, it means that the pipe is closed at one end. So when pipe is closed at one end, that end will create a kind of node in your waves, because it's an obstacle, it's an obstruction that prevents the free movement of the wave that is traveling through the pipes. Okay, that's why the end of the pipe here is node, while the open end is an antinode. And from what we've been treating so far, you can see that between an antinode and the consecutive nodes, we have a quarter of a wavelength. But between a node and another node, or between an antinode and another antinode, we have a half of a wavelength. So which means here we have quarter plus half, and here we have quarter plus half plus half. Okay, we have quarter plus half plus half here. So, and that is what is displayed here. It means the length of this pipe here, that is in second harmonic mode, that is, this one is first harmonic mode, this is second harmonic, and this is third harmonic. So in second harmonic, it means we're going to have this expression. In first harmonic, we have this expression mathematically, since our L, the length of the pipe, equal to lambda over 4. So and in third harmonic, we also have this expression. Now if you look at this expression very well, the relationship between this harmonic series of a closed pipe will go like this. Our F2 will be equal to 3F1, while our F3 will be equal to 5F1. And what this tells us is that in a closed pipe, the harmonic series follows the odd pattern. The harmonic series will follow the odd pattern. That is, the next one, which is F4, will be equal to 7F1, and it goes like that. Unlike the open pipe and the string, where we have natural numbers series. Okay, let's quickly consider some questions here. Like I said, we are looking at calculation. Basically, we are just trying to introduce the formulas. Okay, now let's look at the questions here. This is a past WAEC question also. The question says we have to find the first 3 harmonics in a 2.65 meter long pipe that is open at both ends. That is an open pipe. Also, we have to determine the first three harmonics of this pipe when one end of the pipe is closed. That is when the pipe is turned to a closed pipe again. So we have two things to look at here. So, and we were given the speed of sound in here as 340 meter per seconds. Okay, according to the question, we have parameter length of the pipe is given as 2.65 meter, and the speed of sound in that pipe as 340, the speed of sound in here rather equal to 340 meter per seconds. Now let's first consider the open ended pipe in this situation, like what we've discussed earlier. First harmonic frequency is given as V over 2L, and for open pipe, I believe you can remember that series. And what this simply means is that our V is 340, and we have a 2 multiplied by the length, and playing around this with our calculator, the answer for first harmonic frequency will be 64.2 Hertz. And for our second harmonic frequency, which is also known as a first overtone frequency, and if you remember the series, F2 will be equal to 2F1. So just multiply what you have as value of your F1 by 2, and that is what we did here. And we have this for second harmonic frequency. Also, you can find your third harmonic frequency, which is second overtone frequency, by using F3 equal to 3F1. That is, multiply your fundamental frequency, that is first harmonic frequency, by 3, and you have this value 192.6 Hz. And also, when this pipe is turned to a closed pipe, when this pipe becomes a closed pipe, what are we expecting? So for first harmonic frequency of a closed pipe, we have this equation. So just substitute the values. So our V is still 340, our length is 2.65, and with the help of our calculator, we have 32.1 as the fundamental frequency there. So our second harmonic frequency in this case is 3F1. That is for a closed pipe. We know the harmonic series of a closed pipe is follows odd pattern. So substituting this, that is what we have to do basically here, is to multiply our first harmonic frequency by 3, and we are going to have 96.3 Hz. And the third harmonic frequency, which is second overtone, equal to 5F1. So multiply the value of your F1 by 5, and you have 160.5 as our third harmonic frequency. Okay, let's look at maybe one more question before we call it a day here. Okay, now in this particular question, this question is a past five question, that is 2018 WAEC. This question is question number 10 in 2018 WAEC. The question says, a pipe closed at one end has a fundamental frequency of 200 Hz, full stop. The frequency of the first overtone of this closed pipe is equal to the frequency of the first overtone of another open pipe. So we have to calculate the fundamental frequency of that open pipe, the length of this closed pipe we are discussing here, and the length of the open pipe. The speed of sound in air, according to this question, is given as 330 meter per seconds. Okay, we can easily navigate around this. Let's look at what we have here. These are the solutions for these three questions. Okay, according to the question, for the closed pipe, we have the fundamental frequency given as 200 Hz. So to find the second harmonic frequency, that is a first overtone frequency for a closed pipe, we know the series F2 equal to 3F1, and that is what we did here, multiplying our F1 by 3, and that will give us 600. And for the open pipe, we were told that the first overtone of the open pipe is equal to the first overtone of this closed pipe, which means for the open pipe 2, the F2 will be equal to 600. And using that, we can derive equation for our F1. If F2 equal to 2F1, so our F1 will be equal to F2 over 2. And that is what we used here to get the fundamental frequency of the open pipe. That is, we use 600 divided by 2, because the second harmonic frequency, which is first overtone frequency for the open pipe, is also 600. Dividing that by 2, we have a 300 Hz. Okay, in the second question, we have to find the length of the closed pipe. And for the first harmonic frequency mode, we have F1 equal to V over 4L, and making L the square of the formula, we have a V over 4F1, and substituting the values, our V is 330 and our F1 is 200 for the closed pipe. And playing around that on our calculator, we have the value of our length to be 0.413 meter. And also for the third part of the question, length of the open pipe, we know that the fundamental frequency for the open pipe is given as F1 equal to V over 2L, making L the subject of the formula. We have this, and substituting our value, V is 330, while our F1 is 300, according to what we did in question Roman figure 1, and our length will be equal to 0.55 meter according to the question. That's about the question. Okay, and I think we've come to the end of this explanation, the calculations there. But if you still have any question under this section, that is in standing wave, in stress string, vibrating air column, that is still giving you headache, please feel free to drop the question. You can easily refer to the year in the past question and tell us the question that is giving you headache. We will attempt the question and send the answer directly to you, or post the answer in the comment section. Just drop the question at the comment section. Just before we go, please, if you are here to subscribe to our channel, please do. And whenever you watch our video and you like the video, always click the like button and also click the notification button, so that when we release the subsequent video, you will have access to them. Okay, and before I go, I would like to introduce a physics practical book to us. The name is Refound Physics Practical Book. For those of us preparing for examination like WAEC, NECO, also GC and NECO GC, this book is very, very good for us. And as a teacher in schools also, you can recommend this book for your student. Is a very book. The book is very good, and the book has everything that has to do with practical physics at this level. Please, you can introduce the book to your student. Also, students, if you are in need of this book, because the book contains a lot of practical exercises for WAEC and NECO, also alternative to practical exercises for GC and NECO GC. So for the student preparing for GC and NECO GC, you can as well ask for the book. And if you're in need of the book, you can reach out to us using any of the numbers displaying on the screen here, or our email address. Or if you want the soft copy of the book, it's on Amazon. You can click the link here on Amazon, and you will get the soft copy of the book. Also, we offer some services like online tutorial for students preparing for all the exam listed on the screen here. If you are preparing for your WAEC, NECO, UTME, Cambridge IGCSE, and others, and you really need assistance in your physics, you need one-on-one online tutorial on any channel of your choice, maybe Zoom, Google Meet, WhatsApp, we can attend to you. Just reach out to us on this number, and we'll know how to go about it. And just before I go, please, I would like to repeat this. If you need comprehensive explanation on anything we've discussed so far in this video, because we've only treated calculations here, but every other aspect of this topic, we have a document prepared for students of year 10 to year 12. And you can reach out to us on any of the number displayed on the screen to get this document as just a token. You can reach out to us. We have the document. The document is designed as a student note. It's a very precise and detailed physics document that can help students in any of the examination we've mentioned so far in this video. I want to believe this video will have added something to your knowledge. And if that is the case and you're here to subscribe, please do and like the video. Thanks for watching.